Okay, so long ago in a land far, far away, there were some guys who wanted to know why things fall. Interesting, right? So if I take this and I let go of it, it falls. Why does it fall?
Gravity.
And what everybody says is gravity, and you think you're really smart and you pat yourself on the head and you're very proud. But all you've done is given it a name. What if we gave it the name Melvin? Why did it fall? Melvin. Did that explain anything? No. Just giving it a name does not explain anything. Everybody knew way before Newton came along that things fall. Everybody knows that when you trip, you go down, you don't go flying off into space. So we know that things fall. The question is, why do things fall?
Because of a force pushing down on it? Is that more specific?
Force. Well,
because the Earth has a massive
why?
Because it's massive. The U-ish.
Well, first of all, we still don't know.
Oh.
That makes sense.
There are a lot of theories out there, and none of them have been totally proven. But one that is a good one that, again, it still didn't answer the why totally, but it did answer kind of why, came along with Newton. And Newton was the first one that came along. And Newton came along, and really what happened was he had the Earth and he had the Moon, and he was trying to figure out, like, why does the Moon stay there? He knows the Moon is going around the Earth in kind of a circle. So if it's going in a circle, there must be
an inward force.
An inward force. So we need either an AC that goes along with an FC, of course, and that's pulling in. And so he knows this is happening. He knows this is going around. But he's saying, why? What is there? There's not a big rope that's attached to the Earth and it's spinning around and that sort of thing. But how is this being held up? Well, Newton liked to think. And one of his favorite places to think was out in his apple orchards. And he was wandering around in his apple orchards. And it was fall. Why is fall called fall? Because things fall off trees. Well, in this case, he was in his apple orchard, and some of the things that were falling were
apples.
Apples, and he's out in his apple orchard, and there's a thud happening because an apple's falling, and he's starting to think, is that same Melvin that's pulling the apple down, is that able to stretch all the way out to the Moon? Could it go that far? Could it go even farther? Could it go all the way out to the sun? Could this be the thing that's actually holding everything together? And so he started hypothesizing that yes, there is some pull that's happening from the Earth and the Moon, and they're pulling together, and he called that the gravitational pull. And he said that gravitational pull is providing that centripetal force that's needed. In other words, the acceleration due to gravity all the way out there was providing that centripetal acceleration. And so he knew how far away the Moon was. He knew how long it took the Moon to go around the Earth. So you can figure out how much centripetal acceleration you need. And so he started figuring out, well, what should gravity be if I stretched it all the way out there? And he started noticing that this gravitational force looked like it was proportional to the two masses involved and inversely proportional to the distance in between them. When we measure the distances, we measure from the center of each one. So the distance here is going to be from the center of this to the center of that, not from the front to the front. So that's going to be the distance, and this is all the better he could get. Was he said, hey, this looks pretty good. So if I stretch this out here, if the distance increases, gravity should get smaller. That acceleration due to gravity is getting smaller. And so he turned out that, hey, the data that he figured out using this idea, that the gravity was really close to what the centripetal acceleration needed by the Moon. And he said, hey, this sounds like it has some weight. Maybe this is what ties everything together. Well, the best he could do was the little fish symbol here. That stands for proportional. So proportional, this is the part that's going to be on the test on Tuesday. On here, I'm going to give you some examples of what happens here. And you should be able to look at this formula and figure out what's happening. It's really simple. Whatever change happens to the M, what change happens to the F? Same change. So if M1 is 132 times bigger, then F is 132 times bigger. If M2 gets 96 times smaller, then F gets
96 times
smaller. Anybody have trouble with that concept?
No.
Super simple. Now, the difference is when we get to the D, instead of being on top, D is on the bottom, which means when D gets bigger, F gets smaller. When D gets smaller, F gets bigger. But D is also squared. So if the D is 2 times smaller, the F gets
4 times bigger.
4 times bigger. The 4 because it's 2 squared, and the bigger instead of the smaller because that's on the bottom, that's on the top. So if the D is 10 times bigger, then F is
100 times smaller.
100 times smaller.
Good job, Patrick.
Super duper simple. Everybody understand that?
Yes.
We can all dominate on those kind of questions?
Yes.
Good. So that is the concept that we're looking at, and that was all the best that Newton could get out of this, was he was able to predict this sort of thing, but he was not able to calculate like exactly what these things were. He could not come up with an experiment that could change his proportional weight. So what happens was we had to wait some time. The amount of time we had to wait was 150 years. So Newton's dead, never knows if this is going to work or not. 150 years later, a man named Henry Cavendish comes along. Henry Cavendish comes along, and he's the first guy that can come up with an experiment that can see if Newton was right. What Cavendish did was he took a piece of scrap metal. So this metal is thin, it's flat, it looks like a big long ruler, that sort of thing. At the very bottom of it, he stretches out a rod and he sticks some masses at the end of that. Now, if you've ever played with flat metal like this, if you twist it, it wants to twist back into position. No problem. He's got the top end clamped down, he takes the bottom end and he starts to twist it, and he measures how much force. And he finds there's a nice direct relationship between how much twisting it is and how much force there is. And so he's got this relationship going, he knows what's happening. In his barn, he builds a little room that's about yay big and about this tall, and he seals it all off. It's got a couple little doors that he can move some stuff around, and he's got some windows he can take measurements in. But he's got this all sealed off so that the wind isn't going to affect it because he knows this is going to be very small. So inside this room, if you're looking down from the top, he's got this strapped in at the top, and so it's in here. And what he does is he's got 2 little doors that he can move stuff in, and he sticks in here a big cannonball right next to both of these because the cannonballs have big masses. So then he said, well, if I move these big masses next to these small masses, if Newton is right, then these masses are all going to attract each other. So what should happen is this little mass should want to go toward this big one, and this little mass should want to go toward that big one, and it'll cause this thing to twist. So what happens is he moves the cannonballs in and seals it off again, and it oscillated back and forth and finally came into equilibrium. And when it did, he measured, and he found out, yes, it had indeed twisted. If it had twisted, he could measure how much force was being exerted. He knew how big the masses were. He could measure how far the distance had changed, which means he is now able to change this equation from a proportional into an equality. So he found the big G, or he found the relationship was exactly the same, but to change from a proportional to an equality, we need to add a constant. A constant is a number like pi that's always the exact same number that you use all the time. And what he was able to do, again, if I knew the data for everything else, I can solve for what this is. He called it big G, which is called the universal gravitational constant. So guess where it works?
Universe.
In the whole universe. So anywhere you go in the universe, this works. So that's kind of handy. So big G turns out to be 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. So that's the number, 6.67 times 10 to the negative 11th. You won't have to memorize it. It'll be on your formula sheet. So you'll be able to use that. But that number, just like pi, is always the same number. Every single time you plug in for G, you're going to plug in this number. Now people freak out over the unit, and they say, is that a formula? No, that's just the unit. It has a funky unit because this unit has to cancel everybody else's units out, which means force is going to have to be in newtons. The 2 masses have to be in kilograms, and the distance has to be measured in meters. So that's all there is to it. Very easy number to use. So what this says is you and your neighbor have some sort of gravitational attraction between you two, based on how big you guys are and what's the distance in between you. So why aren't you going thunk together?
Because of the amount of force.
It's a very small
Yeah,
amount.
it's small.
Yeah, if you look at this -11 multiplying by your masses and this small distance in between you,
Super small.
it's going to be a very, very tiny number. So we don't care too much about the attraction between you and your neighbor. That's not very significant. What is significant is when we start talking about larger masses. We tend to be dominated by one large mass, which
The
is
sun.
even closer.
The Earth.
Okay.
That big mass under your feet tends to dominate our world. And so we are attracted very strongly to that big mass underneath our feet. So if we look at that big mass underneath our feet, we start saying, hey, that's really dominating me. So this is our Earth, and this is me standing on the Earth, and my mass and the Earth's mass are pulling on each other, and that makes a gravitational force that I call...
Wait, what?
Actually, you said it in your first word there.
Gravity.
No. I said your gravitational force is the force between your mass and the Earth's mass. So the Earth is pulling you down, and you're pulling the Earth up, but you're pulling each other with your gravitational force. This gives you what force on you?
A weight.
The weight. That's the force I'm pushing into the Earth with, right? So the reason I have weight is because my mass and the Earth's mass are pulling on each other. So this Fg is really the weight. But we know that weight is equal to
Yeah, mg.
mg. Well, this is my mass, right? So if I cross out my mass, what mass is left over? The Earth's mass. So if I want to find out what's the acceleration caused by gravity, that's just going to be big G times the mass of the Earth. And now we have to have the distance between us. Well, you're tempted to look down and say, well, my foot is right on the planet, so the G must be 0.
It's the center of
It's the center.
But it's the center of me to the center of the Earth. Of course, the center of me down doesn't make much difference. But from here to the center of the Earth, that's called the
Radius.
radius of the Earth. So this is really r squared. So I'm going to put a little prime on this because this is G if I'm standing at sea level. And in fact, if you plug in the data for this, you will come up with 9.805. That number look familiar?
Yes.
Yes. So that's where we get the 9.81 if we were calculating it. We also find it just by dropping things and figuring it out, but that's the way we figured this out. So this was going to be what we get here. But if I'm up higher, R gets bigger, G is going to get smaller. And so this is going to be affected by all that. So we call this G prime because this will find the acceleration due to gravity anywhere. And what's really nice is this doesn't just work for the Earth, this works for anywhere. If I'm standing on the moon, I would stick in the moon's mass and I would stick in the moon's radius and I would find that this is about 1.6. So if it's 1.6, that suddenly became much smaller, which means I got a lot lighter. On the moon, I only weighed 30 pounds. That's great. I would have serious hops because I'm used to carrying around 200 pounds and suddenly I'm only carrying around 30. I've got great hops. I can jump really high. If you've ever seen videos of people when they were on the moon, they were just kind of shuffling along and just that shuffling motion would pop them up off the Earth. Off the moon. That was their Earth at the moment. So it pops them and they're just hopping and moving along and it's like, woo-hoo. What would happen if you go to Pluto?
Yes.
You
It's just our
fly.
If we plug in the mass of Pluto and the radius of Pluto, we get something, I don't know exact number, but it's something along here. We can do the calculation later, but
Wow.
it's really tiny. I would weigh about 1.5 pounds on Pluto. So what kind of hops would I have there?
Would you
I think
escape the
we're
gravitational pull of Pluto if you jumped?
If I jump up, it will take me a couple days to come back down.
Oh, okay, so you wouldn't escape the
You would have
gravitational
If-
good hops.
If I
So if I
run,
jump up, it would
if
take me
I
2
run
years.
sideways and leap, I can put myself into orbit.
Oh.
Nice.
Now, it may not be a pretty orbit, but I put myself into orbit.
Sir,
Now, yes.
Sure.
what about Jupiter's gravity?
Jupiter's gravity is bigger,
Much bigger.
and so we get heavier. What's even more fun is if we would go to the sun.
Yeah.
If we go to the sun, suddenly I weigh 5,000 pounds. Would this be good?
No.
No, we wouldn't burn because we'd go at night.
Yeah.
But yes, I would weigh like 5,000 pounds on the sun. So would this be a fun trip?
No.
Yes.
No, because my body is designed to hold up 200 pounds. It's not designed to hold up 5,000 pounds. The weight of me just being me would crush myself down into jelly.
Yeah.
Sir, if you would jump, what happened?
I don't think I'd have much hops on the moon, on the sun.
Would you go like?
No, but if you like drop something, supposing you could hold yourself up, if you would drop something, it'd be like you shot it out of the gun practically, the way it would slam into you.
That's
So,
hilarious.
yes.
Would it make a more? Would it get colder?
Okay, now, moving on, I'd like to show you, and it, yes, sir. Okay, bye. There was an interesting drawing that was drawn a couple hundred years ago. Whoops. I can draw. Here's a mountain, and on top of this mountain we have a cannon that we are pointing horizontally.
Yeah.
So if I shoot this cannon horizontally, of course the cannonball is going to travel in a
Parabolic trajectory.
parabolic trajectory. But if I shoot it faster, it's going to travel in a parabolic trajectory. And if I shoot it faster, it's going to. I'm faster, it's going to. I'm faster, it's going to. I'm faster, it's going to. And faster.
Please excuse the interruption. At this time, teachers, will you please release all band members to the band hall? All band members to the band hall. Thank you.
Okay, so as we see this, we're still moving in a parabolic trajectory, but our trajectory is getting flatter and flatter and flatter. This will work for a while, but as we're going infinitely faster and faster and faster, eventually, is the ground going to look flat?
No.
No, eventually the ground is going to noticeably be curved. As the as the Earth's surface is curved, now we have a problem. So if we're up here shooting our cannon, and the Earth is curved, what's going to happen is, again, when it first comes out, it's going to go in a nice parabolic trajectory down. Then if I shoot it faster, now suddenly I'm killing people on the equator. And if I shoot it even faster, I'm killing penguins.
Yes.
And there is a possibility that if I shoot it at just the right speed,
You might hit
what's
yourself.
going to happen is this is going to come around and I'm going to shoot myself in the back of the head. Now you say that would be really weird. Well, if I duck and get out of the way, what's going to happen to that bullet?
It's gonna go again.
It's gonna go back
It's going to
again.
go around and around and around and around.
So you're not to die.
Now, how much energy did I put into it?
You just move yourself.
I just had to put energy into it initially, but how long is it going to keep going around?
Forever.
Forever, because the whole time all it's doing is
Accelerating.
falling.
So you
What was
stop.
happening here is it was falling, it was falling, it was falling. When it's in orbit, it is
Constantly
falling. But what it's doing is the curve of the fall and the curve of the planet match each other so nicely that I continue falling the whole time, but I never get any closer. Now, if I want to know what speed
Because it's
this
falling
is,
towards
of
the
course
Earth.
we know
Whoa. So when
it
you
went to the next line.
towards the Earth,
Okay, so the AC I know is equal to b squared over r. Now, if I want to know how fast I want to go to make that perfect orbit, what's providing my centripetal acceleration?
B Earth.
The acceleration due to gravity, so this is really
G.
g prime. So if I'm looking for v, r needs to come up, so I'm going to have g prime r equals v squared. To get rid of that, I need to square root that. So this would give me what speed I need to go at to make this nice perfect circular orbit around the Earth. Now, is g going to be 9.81 up here? No, because I'm farther away, so g is going to get smaller. So again, I would just go back to that g prime equation that we talked about before,
Calculate it.
where we can do this, and we can find out what g is and stick it in there, or we could actually do the algebra to combine them and make it into one step if you want, but this is the formula that we come up with. Now, guess who first came up with this idea that we could go into orbits and made this pretty little drawing that's like this? Isaac Newton, 350 years ago. So he came up with this idea that we could put things into orbit and told us how to calculate it, but we couldn't prove that he was right until 1957.
Oh, Sputnik.
Sputnik was launched by the Russians in 1957 using these same formulas, and guess what?
It worked.
They worked, and Sputnik was orbiting for a while, and it was like, hey, this is pretty cool. And once it's up there, how much energy did it take to keep it going? Zero, because how much energy does it take to fall?
Zero.
So once you're at the right speed, you're going to be great. Now, if you're less than this speed, you are going to orbit decay, and you're eventually going to fall in. If you're going greater than this speed, then what's going to happen is you will end up going out. So anything greater than this speed is called the escape velocity. You're going to have to get an escape or
Get the space shuttle out.
Then you'll be lost.
lost in Spain.
Or you will be in Spain.
Yeah. Here we have a question. How many of you have seen astronauts in the space shuttle?
Yes.
Astronauts in the space shuttle are doing what?
Actually, free fall.
They're floating around.
Okay, like when
How many people have seen them float around?
What?
Looks like fun, right?
Yes.
Now, a question that you always ask, and this is great, you ask your mother this tonight when you're having dinner. You say, hey mom, have you ever seen the astronauts in the space shuttle? And she goes, yeah. And you said, they're floating around, yeah? And she goes, yeah. And you say, why are they floating around? And your mother's going to be like 98% of the people on the planet, and they're going to say, because there's no gravity.
They're free falling the whole time.
Several of you are probably thinking that same thing. What? That's not the right answer? No, we've just been talking about when I'm in orbit, I'm doing what?
Free falling.
Free
I'm
falling.
falling. How much do you weigh when you're falling?
Zero.
Zero. That's why they're floating around, because they and the space shuttle are both falling. If you're in an elevator and I cut the cable and you and the elevator are falling and you do a little toe touch off the bottom, you're going to slowly float toward the top. If you just see a camera inside, it's going to look like you're floating. You hit the top and you give a little shove, you're going to float your way down because now you're falling slightly faster than the car is. That's what's happening in the space shuttle. There's lots of gravity. And people are like, no, there's no gravity, man. But there has to be gravity, because if the space shuttle is here orbiting, it's moving in a circle. And anything moving in a circle has to have what pulling it on it? Some sort of centripetal force. And what's providing that centripetal force?
Gravity.
Oh, but you just said there's no gravity up there. You know what I mean? So if there was no gravity where the space shuttle is, then the space shuttle would be going off
Tangential.
at a constant speed in a straight line, not in a circle. The only reason it can move in a circle is because something's pulling in on it, and that's the gravity. In fact, the space shuttle only actually orbits about this high off the Earth. And when it's orbiting at that height, instead of being 9.8, up there it's all about 9.1. Ooh. So I lost 10 pounds. Is that going to make me float?
Yes.
No. What's going to make me float is the fact that I'm falling.
Yes.
Does this make sense?
Yes.
Okay. Now we get to the real purpose of this little drawing that's been here for so long. We're going to draw a person in 5 different spots here.
You can. So it's not funny.
Is this being recorded?
Yeah.
We are going to hear you say
Okay, so here we have a person at point A, point B, point C, point D, point E. A is at the center of the Earth, B is somewhere in the Earth, C is at sea level, D is up on the top of this ridiculously tall mountain, and E is way out here. Now,
How did he get out there?
it doesn't
Escape.
matter the propulsion method, he's there. First, I have to offer this caveat because some of you are going to misquote me here. There is no mountain as tall as D. Okay? If the Earth was really this size, then the Earth's atmosphere would be about as thick as that line is, and the biggest mountains would go about 1/4 of the way into that. So that'd be the equivalent of if we're feeling Bob here and we can feel some of these letters, that was what the Alps would feel like. Okay, so they're not so big. Anyway, there's not going to be a mountain this big. Now, if you look at these 5 guys, Who is going to feel gravity the strongest?
A.
No, C.
E.
A.
Because the
distance
distance
is
is right on the
tiny.
radius.
Because the
Who is
distance
gonna
is
what?
tiny and it's inversely proportional. Exactly.
Now, we know that the acceleration due to gravity, GME over r squared, what's never going to change in these three, in any of these situations?
The radius?
Both G and M don't change. We're on the same planet both times, we have the same G everywhere. So the only thing that does change is
R.
R. And so you're thinking that I'm going to feel the strongest acceleration due to gravity where?
A. The middle. A.
You'd think that.
E.
Yay!
Strongest acceleration due to gravity will be felt at C. Now, this will make perfect sense if you follow the logic here. If we ignore for a moment A and B, and we just look at C, D, and E, well, C, obviously, the gravity here would feel 9.8, no problem. Now, if we look, C is 1 Earth radii away. If we look at D, he's like 2 Earth radii away. So now suddenly he's twice as far away. So if R is 2 times bigger, then G is going to be 4 times less. So 9.8 divided by 4 would be about 2.4, right? So now if we look at this and we say, okay, this is 1 radii, 2 radii, person E is out here about 3 radii away. So if he's 3 times bigger, it's going to be 9 times smaller, so he's going to feel about 1.1. No problem, right? That's easy calculation. That should make perfect sense to everybody. What is different about A and B that wasn't happening at C, D, and E?
They're inside the Earth.
Than the Earth.
Listen to Frank again.
They're inside the Earth.
They're inside the Earth. The other 3 were happening when we were outside the planet. And this is really easy to deal with when we are outside the planet. Because what happens is we pretend like the whole mass of the Earth is located at some point right in the center. We do this because the math is easier. But in reality, C is more attracted to this piece of dirt than it is to that piece of dirt. Because this dirt is closer and this dirt is farther. But these two average out as if they're right in the center. And so mathematically, it's much easier to pretend the entire mass of the Earth is located at a point in the center because the math is easier. But that works out fine as long as...
At this time, please release all football players to the field hall. Football players be released to the field hall. Also, teachers' office block. Please report to the gym at this time. Thank you.
So that works out great as long as we are outside the planet, we can pretend the mass is located at one point. But once we are inside the planet, reality steps in, and when you're at B, the majority of the dirt over here is pulling B this way, but all this dirt over here is pulling B that way. Which means if you're at point A, how much force do you feel? None. Because if you're at point A, I've got dirt that way and that way that are balancing each other out, that way balancing each other out, in and out balancing it out. I have an equal amount of dirt pulling me every direction. So if I could hollow out a little space in the center of the Earth, that would truly be an anti-gravity room.
Mr. Paulson, so you wouldn't need any balance. So
You would be in perfect equilibrium at that point, because I'd have equal mass pulling
If you're
me
in the
everywhere.
center of the Earth.
Mr. Ball,
Is it
would you
centered
be like spinning or
Yeah,
just
it's
like
really hard.
standing
Well, if you're in a little room, you'd just be floating there.
just floating like you wouldn't be like
If
spinning?
you try and spin yourself, if you're wearing a magnet, then you, no, anyway. That's what it is. Okay, that's kind of cool, right? Does that make sense? Now, I wish we had more time because it's even more fun to imagine that we have a hole that we could drill all the way through the planet, and we could find out how fast are we going if we would dive in over here and make it all the way to China. But we don't have time to do that one.
Well, what about to the people that don't go
What are your acceleration increase and what's your middle?
We were talking about all that, but we're not. Anyway, last thing I do want to talk about is there is this neat effect that happens on the planet. This is the, and this of course is the
That's RTH.
Earth.
Earth.
Oh, Earth.
You go Earth.
Like third.
It takes some of you a while. We'll get it tomorrow. Anyway, the Earth is 70% covered in
Water.
water.
Magma.
So we're going to just pretend the whole planet is covered in water because it's easier to show you this example.
Water.
Now, just like we were talking about, we talked about how we pretend that all the mass is located here. And that works out great for
Outside.
the planet. But the planet is fine because it's mostly solidish, at least on the outside, and keeps the liquid part inside contained. But we have this water on the outside. And the water on the outside is really only stuck on by gravity. And so it's stuck there. But the moon has gravity. And so the moon is also pulling on our water. But does it pull equally on all of our water?
No.
No.
When it's
No.
orbiting, it pulls more on different sides.
The water that's over here gets pulled harder than the center of the planet does because this water is closer to the moon than the center of the planet is. So this water actually ends up bubbling up toward the moon. Now what happens is the whole planet gets pulled toward the moon, and so the Earth actually wobbles as the moon is going around it. And so there's a noticeable wobble of the Earth because that moon is yanking it. So the moon is pulling the Earth this way, and the water over here doesn't get pulled as hard as the Earth does. So this water gets left behind over here.
Tides.
These are called tides. Over here we have
High tide.
and over here we
Low
have
tide.
Low tide.
No, this is high tide.
Okay, I
because
get you.
the water is high because it's being left behind. That means the water that is equal to the center of the Earth, the water that's on this side in the middle, this is low tide, and on the back side of that planet is also low tide, which means twice a day we're going to get high tide, and twice a day we're going to get low tide. Now, in a perfect world, you'd think, oh, this is great. High tide should be how far apart?
12 hours.
You'd think they'd be exactly 12 hours apart, but they're not because something's happening. The moon is not actually stationary. If the moon was just sitting there, then the moon and the Earth would pull on each other, and the moon would come crashing in and make a big mess of the Earth. But in fact, the moon is in this beautiful balance between it trying to have some centripetal force and Earth pulling in on it. Those balance out quite nicely. And so we're in this balance, but what happens is, when should we have high tide? When the moon is?
Directly.
It's not exactly directly overhead because water has inertia. It takes it a while to respond to this. So it's actually when the moon is a little past overhead is when we get the highest of tide. But since the moon keeps moving, it takes 28 days for the moon to go around the Earth. We're spinning it around once a day. And so we're whipping around and it's going slowly. So really what happens is high tide is like every 13 hours instead of every 12 hours. Does this make sense?
Yes.
So it keeps going like that. So you can't say, oh, high tide was noon yesterday, it's going to be noon again today. It's not. It's going to be off. So you have to check these little tables. They keep track of it if you like to go fishing or surfing or whatever. Surfing.
Yeah, there you go.
Okay, now, the last part about tides. The moon is not the only thing pulling on the Earth. There's something even bigger over here called
The
The
sun.
sun.
Now the sun is huge compared to the moon.
It's completely unproportionate.
So you'd say, well, yeah, this I couldn't make it on here if it was in proportion. But the sun is enormous, so you'd think it'd have a totally bigger effect, right?
Yes.
Except relatively
But it's
speaking,
distance.
this is much farther
Yeah.
away. And if you remember, the D was squares.
Inversely proportional.
So this one, even though it's much bigger mass, because it's so much bigger distance, it has less of an effect, but it still affects our tides. Now, if the sun is over here and the moon is over here, the sun is shining on the moon, and this is the bright side of the moon reflecting back to the Earth at night. So we see this as a full moon.
Yes.
Now, when we see the full moon, the moon's on one side, the sun's on the other side. Are they helping or hurting?
Hurting.
They're hurting. So what happens is during a full moon, we have the lowest high tide of the month. When do we have the highest high tide of the month?
New moon.
When the moon is over on this side, now the moon and the sun are both pulling together. This is going to give us at the new moon the highest of the high tides of the month. Get in?
Yes, I get it.
And that's how the tides work.
Awesome.
That's just neutral, is low tide. So yeah, the whole tide thing is kind of an important thing because it gives us an opportunity to wash nutrients in and out of that intertidal zone, which is really important for life and stuff. So it's a good thing we got this enormous moon in a nice, perfect orbit. So next time we will talk more about where our planet fits in the solar system, and we'll do that sometime next week when we have some time. So, yeah.